Hello guys, in this video we are going to continue with the global first vector and assembly global displacement vector, and then we are going to calculate the stress concentration factors for each rectangular plate with various um, uh, circular radius. And then we are going to compare these Ansys results and our results in a plots. So before proceeding further, let's recall our previous video. Uh, in the previous video, we numbered our nodes and elements, and then we assign our boundary condition with BCS function. After that, we procure global stiffness matrix with the help of the assembly function. Let's proceed with the assembly global first vector. Let's go to the assembly f function. As an input, we give the extended node list and node list to the function, and we are expecting to get global force vector. So like we did in the previous function, we get the number of nodes and problem dimension, which is 2. And then we initialize our degree of freedoms to counter. Then we create a loop through each node and loop through each dimension to procure our force, global force matrix. So as you know, guys, if our value is equal to 1, that means these nodes is free to move. So for this reason, we increment our degree of freedoms by 1. So the logic of this for loop is like that. Like we discussed in the previous project, in the project 1, if the node is free to move, that means we have no reaction force at that node. So if our degree of freedom is equal to -1, that means this node is not free to move. This node is constraints. That means degree of constraints. So therefore, this node has reaction forces. But in this function, we just want to get the force values for degree of freedoms. That means the nodes that are free to move. So the reaction forces at that nodes is 0 basically. So for this reason, we get the values from the extended node list, and we return back to our main code with the assemble global force vector. So after that, we are gonna calculate our global displacement vector. So we assembly it with the aid of assembly u function. So in that function, basically, we give a extended node list and node list from the main code as an input to this function, and we expect to get global displacement vector. Like we did in the assembling global force vector, we get the number of nodes and problem dimensions value, and we initialize our degree of constraints. So uh, for loop, this for loop is same logic like we did in the force vector. Uh, but at that function, we are looking for to -1 value because we we are looking for the constraint degree of freedoms. So if that node degree of freedom is -1, that means it's constrained. So we increment our degree of constraint by 1 so that we assign the corresponding displacement value from extended node list to the global displacement vector that we assign in the boundary condition. Like, let me show from the presentation. So, as you remember, in that line, we give the displacement value as minus 0.05. And in that point, we give the, in that line, we give the displacement value as 0.05. So we basically assign this value to the global displacement for vector. So after we procure this value, we return back to our main code. Uh, let's continue with the partitioning the global stiffness matrix into sub-matrices to solve the unknown displacements and unknown forces. In partitioning methods, uh, like we did in the project 1, the equation is same. The logic is same, the code is same, the whole thing is same actually. We are doing the same logic in that project. So we found our matrices, and with the help of these equations 3 and equation 4, we will find our we obtain our unknown displacements and unknown weight force. And then we should update our extended node list with respect to our displaced nodes. So for this, we're going to use the unknown displacement matrix because we already know the prescribed displacements like we did in the this like in that line we give a displacement of minus 0.05. In that line we give a 0.05. So we need to include this unknown displacement to the displaced nodes function to get our updated extended nodes. So let's continue with the displaced nodes function. So in that function, as an input, we give from the main code extended node list and vector of displacements, node list, and forces. As an output, we expected to get the updated extended node list. So, like we did in the previous function, we get our number of nodes, and we get our problem dimension, and we initialize our degree of freedoms and degree of constraints. So to update the displacements for free degree of freedom, because we already know for the constraint degree of freedoms, we just need to update displacement for free degree of freedoms. How we can do it? We already found with this formula. Let me show. We already found this with this formula. So we just need to assign this value into the extended node list. So we implement this with the help of for loop. And then we also need to update our forces for constraint degree of freedoms because we have no any reaction forces for the free degree of freedoms. The logic is same, just same with the displacements. We create our for loops, and then if the degree of freedom is equal to -1, that means we constrain this node. For this reason, we increment our degree of constraints and we assign our forces, unknown forces, at constrained degree of freedoms to the extended node list. Actually, updated extended node list. And we return back to our main code with the updated extended node list. After doing all this, we just need to compute the stress distribution and maximum stress value to calculate the stress concentration factor. So how we can do it? Also, we have lastly one uh, function to get the maximum stress. Actually, maximum stress matrix. So in that coloring function, let me check. We essentially get the visualization of stress and displacement distribution on the elements for rectangular plates. So as an input, we obtain our updated extended node list from the main code and node list, element list, and finally number of Gauss points, which is 4. And as an output, we expected to find the maximum stress matrix across all elements. So, like we did in the previous functions, we first define our problem dimension, which is 2. And since we use the quadrilateral elements, our number per elements is 4. And we define our number of nodes and number of elements. We change with the changing dimension of the whole, and then we are gonna calculate our displacements, stresses and strains values for uh, each element in the element values function, and we will go back with the whole matrices. So let's check the elements values function. So in that function, as I mentioned, we will calculate our displacements, stress and strains values for each element. And as an input, we get node list, element list, updated extended node list, and the number of Gauss points per elements from the coloring function. So as an output, we will give to the coloring function the element displacements, element stresses, and element strains. So as we did in all function, we define our number of elements, nodes per elements, which is 4, and problem dimension. And then to calculate the displacement, strain, and strain, we initialize our arrays. So to calculate these values for each element, we will create a for loop that starts with the first elements the to the number of elements. So E stands for the number elements. So first we will store our node list from the element list, that is each elements for each elements which starts to 1 to nodes per elements. So our nodes per element is 4. That means for each element we have 4 nodes. So we will get the that nodes numbers that elements have. So yeah, we get these values, and then we will extract the displacements for the element nodes with the help of the NL matrix that we define in that row. So for this, we create two for loop that I indicates the number of nodes of the current element, and J stands for the direction, that's X and Y, since we have a two-dimensional problem. So in that we have already calculated our displacements and we update our extended node list with the help of the displaced nodes function. So these calculated displacements should get into this matrix to use in this for loop. For displacement matrix, the first column actually first row stands for the current element number, and this I stands for the nodes that is in this element, and J stands for the X and Y, that is problem dimension. And we assign our displacement values. We extract these values from the updated node list, extended node list. And then we will obtain our local node coordinates with the help of the X matrix. And we created a similar for loop with same logic actually. And we get our coordinates to X matrix. And then to calculate our Jacobian, we are going to use this transpose of X matrix, and we will store this information into coordinates matrix to calculate the Jacobian in following rows. So then we will store our displacements vector into U matrix. So with similar logic, we will store our information, displacement vector information into U matrix with extracting this information from our updated extended node list. And then we will start to compute our strains and stresses at our Gauss points that we have 4 Gauss points. That means we have 1 Gauss point for each node. Yeah, we choose actually for to increase our accuracy. We can choose more, but this would cause to increase our computational time. Also, we could choose the uh, less Gauss points, but it would decrease our accuracy. So to calculate our uh, strains and stresses at Gauss points, we create a for loops that will recur our for loop until 4. That starts from 1. So to calculate the epsilon, that stands for strain tensor, we initialize our matrix, and then we will start from 1 to nodes per elements to calculate the Jacobian gradient and the strain values for each node. So to calculate that, first we initialize our Jacobian and gradient matrix that the Jacobian is 2 by 2 and the gradient matrix is 2 by 4. So like we did in the assembly and element K functions, we will use the same function that called Gauss P, and that also we will use the function that called gradient natural to derive our natural coordinates. So first, let's look at our Gauss P function to get the Xi and eta coordinates values and alpha values. Let's check this Gauss P function. So I actually mentioned that, but let's recall that. As an input, we are going to take the number of nodes per elements and Gauss points per elements and the index of that current Gauss point. And as output, we will give our natural coordinates, that's the Xi and eta, and also we will give the weight associated with this current Gauss point. So as you know, in our case, we choose our Gauss point per element. Gauss point per element is 4. So we have table in our let me check, yeah, presentation, that for Gauss point 4 we have these values for Xi and eta and alpha. So um, this this for loop will look at the Gauss point per element values. So in our case, as I said, it's 4. So we are gonna use these values. So for Gauss point 1, in that in that function, for Gauss point 1 to 4, that will do this in this for loop, and for each Gauss point it will go to the Gauss P function and it will take these values and it will return back to the the function, and then this will increase and it will goes to 2, and it will do this until Gauss point 4, and it will calculate for each node and each Gauss points. So after after the calculate our coordinate 1, coordinate 2, which is natural coordinates, that's Xi and eta, we get the values of these, and we will use these to calculate our derivative of natural points. So we will get the data and we will get the nodes per elements in this function to calculate the gradient of natural shape function with respect to our natural coordinates. So our problem dimension is 2, and we initialize our gradient matrix to store our information about the shape function, derivatives of shape function. So let me show this table. This table also used in this code. So uh, let me show from the codes. Yeah, the natural shape function derived with respect to Xi coordinates and then with respect to eta coordinate, and we store this information into result one matrix, and we return back to our function. So and then we are gonna calculate our Jacobian and the gradient. In that, the Jacobian is calculated with the multiplication operation of coordinates, that is transpose of X matrix, and the result one transpose of result one value, that is derivative of natural shape functions with respect to natural coordinates. And with the help of this Jacobian, we are gonna calculate our gradient. That is multiplication of transpose of inverse Jacobian and result 1, which is derivative of natural shape functions with respect to natural coordinates. And then we are gonna calculate our strain value for each node and for each Gauss point. So to find the total strain value for each node, we will add this value to previous strain value. So we are gonna use this formula to find the strain. And I mentioned that this formula is 1 over 2 multiplied by gradient of u, that is displacement, plus transpose of gradient u. So like in this formula, but we have this dyad operation that let's look at. Let's look at. That is the tensor product of two vectors actually. So to calculate the dyadic product, we are going to use our first vector and the second vector. So what are these vectors? Let's look at from this. Yeah. Our first vector is our gradient, and our second vector is our displacement vector. That is for this node, this current node, and plus for this, our first vector is displacement vector, and our second vector is gradient vector. So let's check the what are we doing in this dyadic product function. So we basically multiply these two vectors to compute the dyadic product. As an output, we get our A matrix. So for this operation, we create two for loop that is 1 to 2, that's problem dimension, and 1 to 2, that is also problem dimension. So as an output, we get a two-dimensional matrix that represent our dyadic product of our vectors. Let's return back to our code. Yeah, that one, the A matrix and the B matrix. So with the help of this dyadic product function, we get our stream values for each nodes. And then we calculate our stream for each element with the help of this summation. So when we end this for loop, we get our stream value for this element. And then we are going to calculate our stress values with the help of the constitutive matrix. So let me show this product. Let me show this equation. To find our stress, we should use our constitutive matrix and the strain matrix for this element. How we are gonna calculate this constitutive matrix? So like we did in the previous function that is called element k, we are gonna do the actually same thing. Nothing different. So we called the stress as CI, SI, and we have constitutive matrix function that that does the that does the this this general formula in that function. So we define our Young modulus and we define our Poisson ratio and we compute our constitutive tensor components with the help of this formula. This D matrix actually is the constitutive matrix. So I explained in detail in the previous video in part 2. So as an output, we get the constitutive matrix and we return back to our equation. So like I said, we get the constitutive matrix and we multiply it with the strain and we get the stress value. So like we did in the obtaining strain values, we follow the same logic. We sum them up to find the stress at that element at different Gauss points. So then to recall this strain and stress, we should store these informations. So how we are gonna store this information? This will store for each element and each Gauss points for each directions. So the first stands for the current element, and this stands for the current Gauss points that we get into for loop, which is 1 to 4. So this stands for the 2 by 2 that coming from the problem dimension, and this also coming from the problem dimension. Also, the strain and stress matrices are 2 by 2. So we stored all of these information into strain and stress matrices for each element to use these into visualization of stress and strain. So after storing this, we end our function and we return to our main function that called coloring. So with the help of this element values function, we obtain our displacements, stresses and strains for each elements. So after that, for the visualization, we should scale our view to see clearly the effect of uh, this displacement that we applied in the boundary condition. So in that scale, we basically give a number of 2. If we give the 1, that means the deformation and stress, actually not stress, the deformation representation is will shown in as it is. But to see the clearly how deformed the shape, we should increase this scale factor. So for this reason, we choose 2. We could choose more, but at that, when we choose more, we will see more effect on it. Like it will more stretch visualization. But we choose 2. You can choose whatever you want. It doesn't matter actually. So after that, we create a loop over elements to complete coordinates and stress for visualization. So for this reason, we start from the first element to a number of elements. And we store our node indices in the NL matrices. We get this data from the element list matrix for this element, this current element, from node 1 to node 4. Because we have quadrilateral elements, so that means we have 4 nodes per element. And then we are going to compute our deformed coordinates that multiplied with the scale factor that we decide. So for this reason, we create a for loop for from node 1 to node 4. So it will basically collect the data of x coordinate and y coordinate to represent the deformation. So for this reason, we use updated extended node list data for x coordinates, and we basically scaled up this deformation, and we add this data to node indices so that we create a new x coordinate that scaled up. So for y coordinates, we essentially follow same procedure. So we also scale up our x coordinate value from the updated extended node list, and we add this to the extended node list for these current indices and current elements. So after that, we will extract our stress component from the value that we get from this element values function. For this reason, we first extract the value in the value matrix. so that we are gonna take this x component of stresses into the stress XX matrix. For this reason, we create this for loop from nodes 1 to node 4. And then we also do the same thing for the displacement. For this reason, we also create another for loop, and we get the data of x displacement and y displacement. So for this reason, we use also displacement that we extract from the element values that we compute in. So, and this I represent the current elements, and this J represent our nodes, indices. This represent our X direction, and also it is same for the Y values. That is the one difference from the X values that shows the Y components. So we also collect these data, these two data to visualization. So after that, after doing all these things, after we store all these data, we should plot these stresses and the displacement at x and y direction. We will use a patch. So patch is a object that's that use it for coloring our elements with respect to our nodes values. What does it mean? Let me show from the that is the patch actually. As you can see, in one element, the color that is close to the nodes is different at each corner. So, how we do this? Let me show from node. For example, the stress value at this node for element 37 is different from the node at that corner. So also the value of stress at that node is different from at that node. Also, it is same for this node. It is different from these three nodes. So to visualize that, we use patch objects to clearly show these color differences. For this reason, we create a figure for stress, x components stress, and we use patch object to place this x and y coordinates, and we colored it with stress XX matrix values. So we use face color also, and as a color map, we use jet color map. Also, there are different color map type. You can search for it. So, and then we titled it basically. So, with the help of this, we create the figure for stresses at X component. So also we create a color bar to see the jet colors that is for this. this is the color map. So the highest value is colored with the red and the lowest value colored by the blue. So this same procedure for the x displacement distribution, and we also create another figure for the displacements at x direction, and we also use patch object. The logic is same. We use displacement x matrix to represent our um, distribution. So we also use color map as jet, and also the same thing actually. We do the same thing for the y displacement distribution. So in that, we also use patch object, and uh, we use also color map jet, and we also create a color bar like I showed in that. So like this is an example of distribution of stress xx that we create for uh, the whole radius of 5. And so as you can see, uh, with the help of patch, the colors in elements is differ at each corner, also at each node. So for color bar, the highest value represented by the color of actually red color, and the lower value of stress is represented by the blue color. So as seen, the stresses uh, is higher at this area. So also, so as you can see, at that region, the stress is higher, and the stresses are lower at this region. So it's like that. Let me return back the codes. So after we plot all these three things, we compute and return the maximum stress values as a matrix to the main codes. So let's return back to our main codes, and yeah, we return back with the maximum stress matrix, and then we get the maximum stresses. So we create another matrices to get the higher values at that matrix. And then we get the max value and we store it in max stress. So and then we calculate our nominal stress. So at that point, we use width of, so let me show, yeah, width of plates, uh, the radius of hole multiplied by 2. We subtract this value from width, and we divide this width with this result, and then we multiply it with this stress that we applied to the plate. Let me show. Yeah, as you can see from the question, the stress value that we applied is 100 megapascal. So we use basically the nominal stress equation to find the nominal stress. So with the help of this, we're gonna find the stress concentration factor. So in that point, we divide the maximum stress that we found in the we extract from the coloring function. So we divide this maximum stress value to nominal stress value so that we store the stress concentration factors for each hole diameter. So thus we end our for loop. And then we plot our stress concentration factors that we get from Ansys. So actually, we calculated it in that matrix. So for this reason, we extract our maximum stress values from the Ansys, and we divide it with the nominal stress that we found in this loop. So this is for first diameter of hole, and this is for second diameter. This is for third. So also we represent this with this number. So we found all stress concentration factor and store in this. So after that, uh, in the question, it's asked to plot our stress concentration factor with respect to hole to width ratio. So for this reason, we found the ratio with using the diameter of hole. So in that, we basically divide to the plate width. So we did these for all diameter, and then we create a figure to plot these. So we first use hold on to show these two plots in one figure. So first we plot our stress concentration factor that we found in this code with the help of the finite element method. And then we plot our stress concentration factors that we found from that we extract from the Ansys. So we create a X label and Y label, and we named as a diameter the width ratio and Y label as a stress concentration factor. And we titled it, and we create a legend to show the these lines clearly, and we create our figure final. So after that, to understand how our code is working properly, actually accurately, we compute our percentage errors. So for this reason, we initialize our percentage matrix, and then we create a for loop to calculate our error percentage for each calculated stress concentration factors. So that was all for this problem for our uh, project. So Yeah, thank you for listening.